2,000 atoms exist in two places at once. New quantum experiment shows October 6, 2019. The new experiment demonstrated a bizarre quantum effect on the double-slit experiment on an unprecedented scale. 2,000 atoms exist in two places at once. New quantum experiment shows one illustration suggests the behavior of large and complex molecules spreading like waves in space. Image, Yakov Fine, universe at when giant molecules can be in two places at once, thanks to quantum physics. This is something that scientists have long known is theoretically true. Based on some facts, every particle or group of particles in the universe is also a wave. Even large particles, even bacteria, even humans, even planets and stars. And the waves occupy several places in space at the same time. Therefore, any piece of matter can also occupy two places at once. Physicists call this phenomenon quantum overlap and for decades have demonstrated this using small particles. But in recent years, physicists have stepped up their experiments, demonstrating quantum overlap by using larger and larger particles. Now, in an article published September 23 in the journal Nature Physics, an international team of researchers has made molecules composed of up to 2,000 atoms occupy two places at once. To do this, the researchers built a complicated and modernized version of a series of famous ancient experiments that first demonstrated quantum overlap. Researchers have long known that light, fired through a leaf with two slits, would create an interference pattern, or series of light and dark fringes, on the wall behind the leaf. But light was understood as a massless wave, not something made of particles, so that wasn't surprising. However, in a series of famous experiments in the 1920s, physicists showed that electrons fired through thin films or crystals would behave similarly, forming patterns like light on the wall behind the diffracting material. If the electrons were simply particles, and could occupy only one point in space at a time, they would form two strips, roughly slit-shaped, on the wall behind the film or crystal. But instead, the electrons hit the wall in complex patterns, suggesting that the electrons had interfered with each other. This is a telltale signal of a wave. At some points the wave peaks coincide, creating brighter regions, while at other points the peaks coincide with valleys. Therefore, the two cancel out and create a dark region. Since physicists already knew that electrons had mass and were definitely particles, the experiment showed that matter acts as both individual particles and waves. An illustration shows how electrons, particles of matter, act as waves as they pass through a two-slit sheet. Image credit, Johannes Callier/CC BY-SA 4.0. But it is one thing to create an interference pattern in the electrons. Doing it with giant molecules is much more complicated. Larger molecules have less easily detected waves, because more massive objects have shorter wavelengths that can lead to almost imperceptible interference patterns. And these 2,000 atom particles have wavelengths shorter than the diameter of a single hydrogen atom, so their interference pattern is much less dramatic. To start the double-slit experiment for big things, the researchers built a machine capable of firing a bundle of molecules, bulky things called oligotetraphenylperferids enriched with fluoroalkyl sulfonyl chains, over 25,000 times the mass of a single hydrogen atom, through a series of multi-slotted grids and leaves. The beam was about 2 meters long. It was large enough that researchers had to explain factors such as gravity and the Earth's rotation when designing the beam emitter, the scientists wrote in the paper. They also kept the molecules reasonably warm for a quantum physics experiment, so they had to take into account the heat that pushes the particles. But still, when the researchers turned the machine on, the detectors at the opposite end of the beam revealed an interference pattern. The molecules were occupying several points in space at the same time. It's an exciting result, the researchers wrote, proving quantum interference on larger scales than ever before. The authors wrote, the next generation of experiments with matter waves will push mass by an order of magnitude. Therefore, even larger demonstrations of quantum interference are coming, although it is probably not possible to trigger them yourself through an interferometer anytime soon. First of all, the vacuum in the machine would probably kill you. We giant beings will have to sit in one place and watch the particles have fun,